So, hello my dear, I welcome you again in the series of 2-in-1 series, that is concept plus practice. So, the same subject fluid mechanics, but that part is 4, that means viscous flow over external surface part 4. That means in the fluid mechanics there are two type of nature of the flow. One is the external to the surface and other one is the internal to the surface. So, these are the series of external flow. Why this series is important? Why? Because if you design the airplane, yeah, any flat surface car body, so you must be know about the drag or the lift. So for that one, this chapter is very important for the particular course, BTech course of the students. So before I start that one, I will announce some features of IMS GATE 25-26. So who is a student who are willing to join the online program? These are the some benefits you have to achieve. Some benefit you have to. Okay, what is that? 800 plus hour live classes with a live interaction, theory book, exercise book. In the theory book, there is a content part, that is theory part, and in the exercise book, approximately 4,000 plus questions is there, and that question are divided in the level. That means level 1, level 2, level 3, like that. Okay. Now, the third is the 34 plus year of the GATE question bank with a video solution. Okay. In this one, you have also a video solution, and if you have face difficulty of any problem, that have a QR code, scan it, and the teachers will be guide you. Okay. 12 personalized one-to-one mentorship session and 130 plus online test with the video solutions. Okay. Now, if you want to book a free consultation session, click the link of the description given below, and also you can directly call with this number. And there is another information, that is your Telegram, informatic information, that is your Telegram group. That means join our Telegram group. And what the benefit you have to get? The benefit is scheduled for the free YouTube lecture, like that. Lecture PDF, today's we have to finish that lecture. That lecture will uploaded on the Telegram group. Important updates regarding seminar and webinar. Important notifications like a government job and other PSU job, expert session of the important topic, and also daily cures. So don't miss this. Please join this one. Okay. Now my dear, if you like this video, really today's video, if you like, just like button, share and subscribe to our channel to the another student who get benefited. Okay. Now we'll start the content part. My dear, we'll finish what we have to finish. Just recapitulation of this one. What is the recapitulation? We already finished the Navier-Stokes equation. These are the Navier-Stokes equation. This is the inertial term. These are the body force. These are the pressure. This all equation. This equation is the momentum equation. That means force equation. This is the Newton's second law. This equation is a force per unit volume basis. This equation is a force per unit volume basis. So this is also force. This is your net force per unit volume, mass into acceleration, and instead of mass there is a density, and density is equal to mass by volume. So this is the net force in x direction. This is your net force in y direction. This is your net force in z direction. And there are, along with that, there is a continuity equation. These two equations you can solve any of that condition, situation of that boundary layer. Now, these are already we will discuss what is the above the boundary layer condition and what is the below the boundary layer condition. Already we will discuss in the previous classes. If you know about this one, just go to the previous class. Okay. Now we'll also see that shear stress will vary from leading edge to trailing edge, and while we will moving from leading edge to trailing edge, shear stress magnitude will decrease. That is your wall shear stress. That is your wall shear stress. Okay. Now next one we'll also see from previous lecture ki if you are the fluid which have high viscosity that have a high boundary layer thickness, and the fluid which have a less viscosity have a less boundary layer thickness. Or you can say that a fluid with a slow moving creates a high boundary layer, large boundary layer, and a fluid with a fast moving creates a low boundary layer. This already we'll discuss now. Now we'll be revise today's previous lecture, that means lecture third. What we have to learn about the lecture third? So we have this is the continuity equation, and this continuity equation, this is the continuity equation with respect to u, with respect to y. Okay. Now, what we have to what the result we have to get? We have to get the result that sir, delta by L is less than 1. That means delta by L is very minimum. That means if you compare the dimension of the plate dimension is much higher than the boundary layer thickness. That is the main prime initial assumptions while you have studied the boundary layer theory. So delta by L is less than 1. Now we have analyzed the boundary layer theory from the order of magnitude. So from this continuity equation, we find the order of magnitude of this V is the maximum velocity V infinite is your U infinite delta by L. Delta is what? Boundary layer thickness. L is your plate length, total plate length in axial direction, that is flow direction. Now, then we have to learn the momentum equation. And which direction? Y direction momentum equation. So from the previous classes, we have to conclude that if you apply the momentum equation flow over flat plate in a y direction, that means a transverse direction, perpendicular to the plate direction. So these are the y momentum equation, Navier-Stokes equation. These are the y momentum equation, and we all are applying the equation within the boundary layer. Okay, within the boundary layer. So this within the boundary layer there is a viscous zone. So this term will always present. Now, my dear, see this one. This is your acceleration. This is your acceleration term, and these are the diffusion term. Diffusion of what? Momentum disturbance. Why? Because there is a viscosity is there, and we are already conclude that the diffusion in axial direction, momentum disturbance, that means disturbance of a momentum, will diffuse in axial direction is much less than the diffusion of a momentum in a transverse direction. That's why this term is neglected always. That means the term which is related with dou square by dou x square will be always neglected as compared to the term which is related with the dou square by dou y square. Why? Because this gives the diffusion in a transverse direction, and this gives the diffusion in a axial direction. So axial direction diffusion is very minimum as compared to the diffusion in a transverse direction. So we can neglect it. Okay. So we can neglect it. Now we also conclude that the pressure gradient, that means the pressure gradient, it will be negligible. Okay. That means pressure is not a function of y. That means along a particular y direction, along a particular y, that means if you take a any point at y, that means if there is a plate is there, Now if this is your y direction, now you take any y distance, take any y distance from the plate. So at any y distance from the plate, pressure is not changing. So pressure is not a function of y. That means variation of pressure in the direction normal to the surface is negligible. We already conclude in the third lecture. Okay. That means pressure is the function of x. Why? Because generally pressure is the function of x and y, 2D flow. But in this y momentum equation conclude that pressure is not a function of y. So pressure is not a function of y, that means pressure is the function of x. So if the pressure is the function of x, so what is the pressure gradient partially, that is equal to ordinary pressure difference. This is your partial pressure difference with respect to x, and this is ordinary differentiation. So if there is a one variable only, so it is ordinary differentiation. We'll use this term into a x momentum equation. Why? Because instead of dou p over dou y, if you apply the momentum equation in x direction, we can get dou p over dou x. So dou p over dou x, we have to directly put dp over dy. Why? Because from this conclusion, we can say that pressure is the function of x only. So we can write like that. Now, so that what is the previous conclusion is that that delta by L is very less than 1. Delta by L is very less than 1. They conclude that Reynolds number over the entire, this is an average Reynolds number over the entire plate, is very high. We will correlate. See, these two are the similar things. These are the similar things. So if delta by L is very less than 1, Reynolds number over the entire plate is very, very high. These are the very important assumptions in the boundary layer. Okay. Now, what, and then we have to apply, then we see that dou P over dou Y is equal to 0. That means pressure is not a function of Y. This is what, beta? This is the Y direction momentum equation. This is the Y direction. Why? Because if the Y direction momentum equation, we conclude that dou P over dou Y is equal to 0. Why? Because the pressure gradient is much dominant over the viscous term and inertia. These are the inertia term and these are the viscous term. And the inertia, if you compare the pressure gradient over the inertia term, pressure gradient is much dominating over the inertia term. And if you compare the pressure gradient term over the viscous term, pressure gradient term is much dominating over the viscous term. So these two are neglected. So dou P over dou Y is equal to 0. That is your momentum equation in Y direction. Now, and then we see that if the momentum, that means pressure is not a function of Y, pressure is not a function of Y, that means pressure is the function of X. So if the pressure is the function of X, dou P over dou X is equal to dP over dx. That means, what this says that? That means for a given X, value, that means if you take any X distance from the leading edge of the plate, the pressure in the boundary layer, is equal to the pressure in the free stream. Yes. Why? Because pressure is not a function of Y. That means if you take at any Y1 value from the plate, take any Y2 value from the plate, take any Y3 from the plate, this is not varying. That means pressure, what is the pressure of the free stream? This is the above the boundary layer, the stream is free stream. So what is the pressure within the free stream? The same pressure is the boundary layer. The same pressure is the boundary layer, in the boundary layer. That means what is the pressure in the free stream is the same as the pressure in the boundary layer. That is the conclusion of the Y momentum equation. This is a very important conclusion. That means the pressure gradient doesn't change with respect to Y. Now my dear, we have to apply then X direction momentum equation. What is the X direction momentum equation? That is the X direction momentum equation. U dou U over dou X plus V dou U over dou Y is equal to nu dou square U by dou X square plus nu dou square plus dou square U over dou Y square minus 1 by rho dou P over dou X. Okay. Now, take this term. What we have to conclude just now? We have to conclude that this dou P over P is the function of X. P is the function of X only. So P is the function of X. That means dP over dx is equal to what? dP. P doesn't change with respect to at a particular X value along the Y direction. So P is precisely, you have to write that P infinite like that. There is a P infinite, so all the point there is a P infinite. So P you have to write P infinite. Now we will check, we will identify what is a dP infinite. That means the change in pressure in the free stream with respect to X. What is the value? So flow over flat plate outside the stream, what is that? If there is an outside stream, this is the outside stream. This is the outside condition. Na beta, P infinite is what? Outside condition. So what is the outside stream velocity? Outside stream velocity is U infinite, and it is in which direction? X direction, that means I direction. This is I, this is J. So U infinite is equal to what? U infinite I, that means X direction. Now, so flow over flat plate outside stream is U equal to U infinite I. And mind it, outside region is inviscid region. So you can use the equation of inviscid flow. You can use freely outside the equation of inviscid fluid. What is the equation of inviscid fluid in the fluid mechanics? There are two equations. First one is the energy equation, second one is the momentum equation. First one energy equation is the Bernoulli equation you can use, or you can use Eulerian equation. You can use Eulerian. Why? Because Euler's equation also we can use in the inviscid flow. Okay, in the inviscid flow. So flow over the flat plate, that means outside stream, U is equal to U infinite I. So we can use the Bernoulli equation outside at any point, any 2 point, That means you have to take this point. What is the energy equation at this point? P infinite plus the kinetic energy at this point. What is the kinetic energy of this point? Half rho u infinite square. So half rho u infinite, this is constant. Now, if you differentiate with respect to x, why? Because we have to identify the pressure gradient with respect to x. df infinite by dx plus rho, if you differentiate it, rho u infinite dou u over dou x is equal to 0. Constant integration 0. Now, my dear, since we are analyzing the flow over flat plate, and flow over flat plate, the velocity is fixed. Why? Because streamline is a straight line. It is not a curvature. But see, if there is a, what is the main difference between the flow over flat plate and flow over around the cylinder? So flow over flat plate, beta, the u infinite is constant. Free stream velocity is constant. But flow over the circular cylinder, this point, always the velocity is u infinite is not constant. Not constant. Why? Because there is a curvature. So by default, the flow over flat plate u infinite is fixed. Why? Because there is a straight line. So all the points have a velocity is fixed. So the velocity is fixed. That means d infinite by dx is equal to 0. So d infinite by dx is equal to 0. That means dp over dx is also 0. See the beauty. That means flow over flat plate. Flow over flat plate. Flat plate, very important. dp by dy is equal to 0, and also dp by dx is equal to 0. That means pressure is not a function of x and y. That means, hence, this is very important, I am telling you, very important. What is that? Hence, flow over flat plate, the pressure remains constant. Pressure doesn't change. Pressure doesn't change, constant. It is not 0. Pressure is constant. Either over the pressure constant over the entire plate. Over the entire plate. That means leading edge to trailing edge, pressure throughout constant, both inside and outside boundary layer. That means there is a main conclusion. Someone asks you, if there is a flow over flat plate, the pressure over entire plate remains constant, either you are considering outside or either you are considering inside the boundary layer. Inside the boundary layer. That is clear? So this is your main conclusion, That means pressure doesn't change. Pressure is constant, not 0. Pressure is constant, either inside or outside over the entire plate. But it is not in the case of closed flow within the internal flow. This is the external flow. So that is the subtle concept. Someone asks you, what is the difference between the flow parameter of the flow over flat plate and flow within the pipe? So you can say that, sir, flow over flat plate, pressure remains constant over entire plate, either inside the boundary layer or outside the boundary layer. But in the case of internal flow, pressure always varying. So my dear, there is a chance of a curvature flow over the round curvature part, also the pressure will vary. Why? Because u is not 0. Over the curvature, u is not 0. So pressure will vary. So due to the pressure vary, it may be adverse condition or favorable condition. So maybe the boundary layer separation. So flow over the curved surface may be the boundary layer separation. But in this case, we are not bothering about the boundary layer separation. Why? Because pressure remains constant. It is not at any point there is an adverse pressure gradient. So flow over flat plate, it is not like that. Flow over the, so external surface have a two nature. One is the flat surface, other is the curved surface. So over the flat surface, the pressure remains constant at each and every point over the entire plate. But over the curved surface, flow pressure will change from one point to another point. So there may be a boundary layer separation, but in this case there is not a boundary layer separation. That is very important thing. Okay. Now, so essentially this also term is 0. Okay, this is 0, and this is the inertial term, this is the viscous term, and this is your pressure term. So the pressure gradient in AX direction is also 0. Now we know that the axial diffusion of a momentum disturbance is very minimum as compared to the transverse diffusion. So this is 0 as compared to this one. So only left with 1, 2, and 3. That's it. Now you have to take the order of magnitude. So what is the order of magnitude? U infinite. What is the order of magnitude? U infinite. So U infinite square. What is the order of magnitude? X is L. What is the order of magnitude? V infinite. What is the order of magnitude? U infinite. What is the order of magnitude of Y? Delta. What is the order of magnitude is property of same mu. What is the order of magnitude of U? U is U infinite. What is the order of magnitude? Y square is delta square. So these are the order of magnitude. Now we know that this thing. This already know that in the previous classes in the continuity equation. This is your continuity equation. You can easily find V infinite is U infinite delta by L. So put this value here back. Put the hair back. So put this value, rearrange it. So if you rearrange it, so these two terms are essentially same. This term and this term, if you take order of magnitude, these two are same. So from the concept of order of magnitude, if these two terms are same, so you can take either of any one. So either of any one, you have to take this one. So this two term if you take, so this is U infinite square divided by L. That is the order of magnitude of mu U infinite by delta square. This one U is cancelled. So this is your main equation from the X momentum equation. This is important. That means delta square by L is the order of kinematic viscosity divided by U infinite. Now we have to further consider this one. So this one, so delta square by L is the order of mu by U infinite. Now you have to intuitionally multiply with 1 by L. So this is what delta square by L square is the order of magnitude of 1 by U infinite L divided by nu. So mu into L divided by nu is the average Reynolds number over the entire plate. That means delta by L square root, delta by L square root is the order of 1 by Reynolds number. This is very important. That means this is the now point is that there is a similarity between these two. That means we already proved that we already say that if delta by L is less than 1, so Reynolds number is greater than 1. So these are two are the same things. If that means if you assume delta by L is less than 1, automatically this condition is satisfied. Delta average Reynolds number is higher. That means see this beauty. You can prove like that. See that means. See, that means what is the delta by L is 1 by R square by R total Reynolds number square root. So if we decrease the delta by L minimum to minimum, the Reynolds number is maximum to maximum. That is proof. That means these two things are similar. These two things are similar to each other. That means delta by L is the order of Reynolds number per power minus 1 by 2. Clear? Now, that means there is a one. What is the conclusion then? The conclusion is that, sir, delta. Someone asks you, sir, delta by L is less than 1. So Reynolds number is greater than is how? This is the proof. That means delta by L is less than 1. There is a same thing says that Reynolds number is greater than 1. That means you have to analyze the boundary layer equation, boundary layer theory. The boundary layer theory only valid due to this condition. Otherwise, the boundary layer theory does not exist. The boundary layer theory says that delta by L is less than equal to 1, less than 1. Automatically, the Reynolds number, average Reynolds number with respect to L is the characteristic length is larger. And there is second thing, boundary layer theory doesn't exist in the boundary layer separation. So if there is a boundary layer separation, there is no any existence of a boundary layer. The boundary layer theory is valid only with no boundary layer separation, and other one is delta by L is less than 1 and the Reynolds number is higher and higher. So very important, I'm telling you, 99% student doesn't know this concept. 99% student doesn't know this concept, doesn't know. If you can ask anyone, okay, sir, if the delta by L is less, what is the prime validification? What is the prime validity to satisfy the boundary layer theory? That is your answer. Now, so if you know the boundary layer theory, so what is the importance? That means what the from the knowledge of a boundary layer theory, what you have to do? You have to do the easily calculate the shear stress of the plate. The motive of the boundary layer, you can calculate the drag and lift. Someone asks you, what is the motive of the boundary layer? What is the use of the boundary layer? What is the use of a boundary layer? The boundary layer of use to calculate the lift and drag. That's it. Clear? And when the boundary layer is valid, when delta by L is less than 1 or Reynolds number is high. Then a larger Reynolds number and lesser delta by L ratio. In that condition, the boundary layer theory will be valid. Clear? Now, so what is the wall shear stress? Tau wall is mu du over dy. Why? Because we have to take the fluid as a Newtonian fluid, already in the analysis, and du over dy. And y is equal to 0. Why? Because we have to taking at the wall. This is the y. So y equal to 0, it is at the wall. So at the wall, so what is the order of this mu? What is the order of u? U infinite. What is the order of y? Delta. Now, so if you non-dimensionalize the wall shear stress, you have to introduce a one term known as skin friction coefficient. Yeah, friction coefficient. What is that? Friction coefficient is the ratio of the wall shear stress to the dynamic pressure. These are the unitless. This is also Newton per wall shear stress, Newton per meter square. This is also Newton per meter square. This is the wall shear stress. This is the dynamic pressure. Both are the same unit. So it is a non-dimensional number. So wall shear skin friction coefficient, wall shear stress divided by half rho u infinite square. Now, what is the wall shear stress? Order of mu u infinite by delta. Mu u infinite by delta. What is the order of this one? So we can neglect half. In the order of magnitude, you are not considering the numerical value. So what is the order of magnitude? Rho u infinite. Rho u infinite. Now u infinite cancel. So this is a mu rho u infinite delta, and that means that means nu by rho is what? Mu, and mu is divided by u infinite delta. U infinite delta. Now my dear, we know this thing, delta square by L, y momentum equation, x momentum equation. See, delta square by L is the order of mu by u infinite. Delta square by L is the order of mu by u infinite. So we can use this equation from here to analysis. So we know that delta square L by mu infinite is the order of mu infinite by mu is the kinematic viscosity divided by free stream velocity. So at any local x, we have to find, there is a plate and we have to find at any location. So at any local x, put L instead of x. Why? Because this is at x value. You have to find at x value at any local point. Locally you have to find. So at any local, so this is entire plate and you will find at any location, put L instead of x. Put x instead of L. Okay. So delta square L is the order of nu u infinite. So what is the delta square? X nu infinite. So what is the delta order? Root under x nu by u infinite. Now, so from here, this is very important. So this is very important, my dear. Delta is the order of root x. That means if x will increase, the boundary layer thickness will increase. The boundary layer thickness will increase. That means at this, let's suppose this is x1 distance and let's suppose this is x2 distance, and at x1 distance there is given delta 1 and you have to find the x2 distance. What is delta 2? You can use this relation. That means delta 1 by delta 2 is equal to a square root of x1 by x2. And you can find the boundary layer thickness at any location. This is the importance of this lecture. Okay. Now my dear, so if you find the local skin friction, that means there is a local skin friction coefficient. Yes or not? Local skin. So local skin friction. So these are the delta. Okay, some distance. So what is the local skin friction coefficient? 1 second. Okay. So there is this is your average. CF is the average. We have to find the local at any point x. We have to find at any point x. So we have to find at any point x. This is your what? CFX. CFX, CF local. That means CF skin friction coefficient at any location x. So CFX is called local skin friction coefficient. CF is called average skin friction coefficient. Average, that means throughout the plate. Throughout the plate. Okay. So CFX is mu u infinite delta. Mu u infinite delta. And what is the delta? Delta you already know, right? Delta is equal to what? Delta is the order of square root of x mu u infinite. Delta is the order of square root of x mu u infinite. Put the value here. Put the value here. Rearrange it. You rearrange it. So after rearranging, you can get that this is same as the square root, Rex square root. If you're rearranging like that, please see. If rearranging, put all the rearrangement and then you see that. That means this is called local skin friction coefficient. Hence, very important. Hence, the local skin friction coefficient is the order of Reynolds number 1 by square root of Reynolds number. 1 by square root of Reynolds number. So, and if you solve by the Blassier solution, just now we have to look at from the next slide. If you solve this one, this is your 0.664 Rex by power minus 1 by 2. And if you find the average, this is your local. So if you find the average, just multiply with the 2. How? See, what is that? If you find the average skin friction coefficient CF over the entire plate, integrate 0 to L CFX dx. And you know that the CFX x is equal to 0.664 Rex per power minus 1 by 2. Put the value here, take outside from the integration 0.664 divided by L, and here Rex minus 1 by 2 dx. Now, same 0.664 divided by L 0 to L, and put the Reynolds number, local Reynolds number U infinite x by nu to the power 1 by 2. Now, U infinite constant flow over flat plate, mu is constant. Why? Because it is a property outside. So this is your 0 to L x to the power minus 1 by 2 dx. Now if you integrate, this is your value. If you just integrate it, this is your value. So from comparing these two, you can conclude that, sir, this is your average skin friction coefficient is always twice of the local. Similarly, if you study in the heat transfer, the average heat transfer coefficient, there is a term, average heat transfer coefficient is equal to 2 into local heat transfer coefficient. Like that, if you say the shear stress, average shear stress is equal to 2 into local shear stress. All the points you have to consider like that, okay? Nusselt number, average Nusselt number is also in the heat transfer. Nusselt number is equal to 2 into a local Nusselt number. Like that, always multiply with the 2 with the local, you can get the average value. Okay, now next. So I will intuitionally put here, there are two things. One is the friction coefficient and other one is the drag coefficient. What is the difference? Sometimes in the interview they can ask you, okay, what is the subtle difference? What is the difference? How to calculate? Just in a 2 minute, someone says that you go on the board and just try to understand to me what is the difference between friction coefficient and drag coefficient. In the interview they can ask you, okay, please take a marker, go on the board and try to explain what is the difference between how to calculate the friction coefficient and drag coefficient. So for that one, this slide is very important. How? See, first one is that, see, friction coefficient is defined by the shear stress. Yes, if you calculate the friction coefficient, my dear, if you calculate the friction coefficient, you must have the knowledge about the wall shear stress. That is one thing. So friction coefficient is defined by the shear stress at any point x. This is very important. That means this CFX you can find locally, but coefficient of this drag coefficient you cannot find locally. It is always find over the entire plate, but this CFX it will be find at any point of the plate. Very important. So that in the many, you can see that in the CF you can put X value, but in CD you never put X like that. Why? Because it is not defined as a local. It is defined as a total, but it is defined as a local. Very important. That means CFX is find at any point of the plate, but the coefficient of discharge you can find the total. That means you must be have to integration use. In this case, integration will be used. Say, number second. So if there is a plate, if you find at any location x 0 to x, so this is your value CFX. And what is the CFX local? Tau wall divided by dynamic pressure. So CFX you have to calculate the average. First you calculate the local, then you have to calculate the average value. Local you have to calculate at any point, then you have to integrate 1 by L, 0 to L CFX, then this is your value. Clear? But if you calculate the drag force, you need not be bothered about the shear stress. You are bothered about the drag force. And this drag force over the some length of the plate. That means over the some length. It is not at a point. This is at a point, at any location at a point. But this is at over the some range of the plate. That means you must have a knowledge about the dimension. So if you find the sum, so you have to select the differential element of the plate of a dx length, and width is 1. You take the width is unit perpendicular to the board. So CD is equal to coefficient of drag is equal to coefficient drag force divided by the force. So what is the force? This is pressure into area. What is the area over the entire plate? What is the area? Length of the plate into the unit width, L into 1. So if you calculate, this is a 1.3, similar thing. 1.33, here 1.32. So same thing is there. 1.33 divided by RL pe power 1 by 2. Here same, 1.328 divided by RL power. So CD and CF are same value over the flat plate. Over the flat plate, coefficient of drag and coefficient of friction. That means friction coefficient and drag coefficient are same value approximately. Okay. And then how to calculate this CD generally is to find the drag force. To find the drag force, just to take the wall shear stress, and that wall shear where it is acting, this acting over this entire length. This some length of the plate. So what is the some length of the plate? This is the dx length perpendicular to the board, dx into 1. Just to integrate. So wall shear stress is given in the question. Wall shear stress is given. Just to integrate it, put the here, just calculate it, find the drag force. So what is the subtle thing is that? Subtle thing is that, sir, we have to find the friction coefficient over the any point, but the drag coefficient we have to find over the entire length of the plate. Yes, some length of the plate you have to find. That means in this one, the elemental part of the surface of the elemental part you have to understand like that. But it is in this one there is no need for the elemental part. There is a at the point, at the local, at the point, at the location, any location. It is not at the some length, but here it is a some length. This is very important, I'm telling you. Okay. Then there is another concept, boundary layer over the flat plate. What is that? See, this is your flat plate is that there is a boundary layer. There is a boundary layer thickness. This is the plate length, the uniform velocity u. So what is that flow over flat plate? This is the equation. Boundary layer. What is the boundary layer equation? The third question is that someone asks you, what is the boundary layer equation? The boundary layer equation is that first one is the continuity equation. Second one is your momentum equation, which is in x direction, pressure term is 0, and the diffusion in, this is your diffusion in y direction, not x direction. This is your dou square u over dou y square. I've got diffusion in x direction is negligible. Diffusion in x direction is negligible, na? Diffusion in x direction is negligible. See, diffusion in x direction is negligible. So this is only, okay, mu dou u square u by dou y square. This is very important thing. So this is the second equation of boundary layer, and third one is that y direction. So dou p over dou y is equal to 0. Y direction equation, and this equation, this is very important. This is the third question. Someone asks you, what is the equation of boundary layer? Sir, first is the continuity equation. What is that? Dou u x, dou u by dou x plus dou u by dou v by dou y. Second one is the momentum equation in x direction. What is that? Sir, u dou u by dou x plus v dou u by dou y is equal to mu dou u square by dou y square. That's it. Someone says that other term is negligible. That means the pressure dp over dx is negligible. Change is negligible, and also the axial diffusion term is neglected over the transverse diffusion term. That is okay. Third one is that, sir. Third one is what? Third one is the y momentum equation. What is the y momentum equation of the boundary layer? Boundary layer dp over dy is equal to 0. And fourth question, under which condition this equation is valid? Delta by L is less than equal to 1, and the Reynolds number, average Reynolds number over the entire plate is much higher. Fifth question, what is the boundary condition. What is the boundary condition? Boundary condition, please look at the boundary condition. X is equal to 0, leading edge. X is equal to 0, leading edge. What is the velocity? U infinite. At x is equal to 0, what is the velocity? U infinite. At y is equal to 0, on the plate, what is the velocity? 0. Y is equal to 0, that means this is your no slip condition. This is your no slip condition. So at the y is equal to 0, that means on the plate there is no any tangential velocity. This is 0. At y is equal to infinite, that means you can take outside. So at y is equal to infinite, u is equal to u infinite. These are the condition of a boundary layer. These are the condition of a boundary layer. Okay. Now next, this is your Blasius equation. What is the Blasius equation? This is very important. Someone asks you in the interview, ki beta, what is the Blasius equation? So first thing, 90% of students doesn't heard. Sir, what is that? Oh, what is the Blasius equation? I don't know. Simple thing. See, my dear, Blasius equation is what? See, there are two differential equations, and that are the partial differential equation, and that is very difficult to solution. So Blasius says, what is the Blasius equation develop? This equation is by transforming the partial differential equation. This equation will transform. That means this two partial differentiation equation will transfer into a single ordinary differential equation. So first one, someone asks you what Blasius equation is, the partial differential equation, yeah, ordinary differential equation. You can say that, sir, Blasius equation is always an ordinary differential equation. And what is that? Sir, if this is the equation by transforming a partial differential equation into the ordinary differential equation by introducing a new independent variable. That means you have to take the new independent variable and then you have to convert the partial differential equation into the ordinary differential equation. That ordinary differential equation is Blasius, and this is this one. That means you have to take the new variable, and due to this new variable, you convert this partial differential equation into the ordinary differential equation. That is your Blasius equation. And Blasius is the student of a Prandtl. And Prandtl number, the mechanical student will study Prandtl number in heat transfer. So this is the Blasius equation. Blasius is basically mathematician. So this is our Blasius equation. And Blasius equation is what? What is the nature of this equation? Nature of this equation is third order non-linear. This is a third order. See, non-linear equation. This f is nothing. This is a new independent variable. And all the term are the ordinary differential equation. So from this, if you apply this boundary condition previously, if you apply this all boundary condition, then you have to solve the delta is equal to 5x Rex. That means delta is directly proportional to the x power 1 by 2. Already we have to prove it. Without any known equation, we already proved that. See, this is the beauty of non-order of magnitude. We already proved that delta is directly proportional to 1 by 2. Without any numerical different equation solving. Only the concept of order of magnitude, you can get that sir, delta is the order of x power 1 by 2. Yes, from the equation you can also say that sir, delta is the x power 1 by 2. So these are the boundary layer thickness. Now the wall shear stress is inversely proportional to 1. So wall shear stress is inversely proportional to root x. Delta is directly proportional to root x, and local skin friction is inversely proportional to 1 by root x. 1 by Reynolds number. Root under 1 by, that means this is your 1 by x root x. This is also 1 by root x, but this is a directly root x. So unlike boundary layer thickness is directly proportional to square root of x. Wall shear stress and local skin friction coefficient is directly proportional to the x power minus 1 by 2. So that is the very memorable things. You can always remember like that. So delta is directly proportional to a square root of 1 by 2, square root of x, square root of x. But wall shear stress and skin friction coefficient is inversely proportional to a square root of x. That means if x will increase, the boundary layer thickness will increase. If x will increase, the boundary layer thickness will increase, but if x will increase, wall shear stress decrease, and also the local skin friction also will decrease. So the local skin friction and wall shear stress gives the same nature, but the delta gives the opposite nature. That's why in the first slide, we already discussed that the wall shear stress is decreases as x will increase. See, x will increase, wall shear stress will decrease. Similarly, Similarly, the local skin friction coefficient also decrease. But if X will increase, the boundary layer thickness will increase. So I hope you understand this concept. Now, my dear, in the next series will discuss the displacement thickness, energy thickness, and momentum thickness, and some implication of the practical situation. So up to that, thank you. Bye-bye.